Everyone. I am Fukosi Marivate, the Chair of Data Science at the University of Pretoria, and I run the Data Science for Social Impact Lab. Today we're having our second set of seminars. Today it's a webinar. The previous one was a AI workshop that we held with the Swedish Embassy. Thanks for joining in today. It's really great. Today we have Moseli Mots'oehli. He is a final year Ph.D. student at the Department of Computer Science at the University of Hawaii in Manoa. Before coming to the University of Hawaii, he completed a bachelor's and master's degree in actual science and also data science here at the University of Pretoria under the supervision of Dr. Anna Bosman and Prof. Johan de Villiers. It's great to have him also as an alumnus coming to give us this chat in terms of the seminar series. Just for context, we run the seminar series in the second half of every year. This year was a bit tougher. We started a bit later because during the winter we had the Design Justice AI Institute. I will put some links to these if you want to go watch some of the recordings. It was recorded, it was 2 weeks. So we had to take a break after that. And then we restarted on the 30th of September with the workshop with the Swedish Embassy and AI Sweden. And then now we've got this webinar, and we should have 2 more before the year has ended. So thanks everybody for coming through. So yeah, I will hand it over to Moseli. He will be talking about towards safer driving on Southern African roads through assistive and autonomous annotation and driving. Thanks, Moseli. You can, I guess, switch on your video and then share your screen as
well. Thank you, Vukosi. Can you hear me?
Yeah, we can hear you. And just for context for people, I think the speaker normally speaks between like 30 minutes to 45 minutes, and then after that we do Q&A. You can. We don't have a video yet, but you can share your screen as well.
Okay. On it. Okay. Please let me know when you can see my screen. Let me know if you can see my screen.
Yeah, we can see your screen.
Okay, perfect. Okay.
Yeah, I think you just have to click slideshow.
Thank you.
All right, go ahead.
Okay. Oh, hi, everyone. My name, Vukosi has kind of introduced me very well. Thank you, Vukosi, for that. So essentially, yeah, Moseli Mots'oehli. I've been at UP before for a couple of years, and then I came to the US to study computer science and focus on some really cool research. So I'll kind of take you in terms of where my research is right now, and I'll kind of try to paint or tell a story in terms of how I got to where I started off my research journey to where I am, while at it trying to show what I'm trying to do towards autonomous driving and promoting safety for South African roads. So for a start, I started off studying computer science, actuarial science at UP. And then that was 2012, 2014 finished, moved on to financial engineering for a year just to get the honors. And then after that, UP introduced the data science track and the master's by research and mini dissertation. So I kind of went on to that because I've always seen, once AI was a thing, I have kind of realized I want to do the switch. So that was a great opportunity to do the bridge between actuarial science and computer science. So I went that track and I did that for 2 years under the supervision of Anna Bosman and Professor de Villiers. After which I came to UH in Hawaii to do my master's, and I worked on fish segmentation for the most part while I was here. So essentially trying to figure out if you have a lot of fish, seeing all the fish, identifying their species and the size of each fish. So most of the work I do now stems from the knowledge I gained from that. And then 2021, I graduated from my master's in computer science here and then started the PhD. And I've since focused on active learning, label noise, and general computer vision. But I'll explain what each of those are as we go forward. And on top of that, I do lead the data science department at the Shard in South Africa. We consult with most of the financial industry companies in terms of providing solutions that are AI-based or analytics. So yeah, that's it. That's me in a nutshell. So why is this an important problem? As you know, every day you drive in Gauteng, the N1, always accidents all the time. And some of these are quite avoidable accidents, but then without the right technology to help, you're not able to, because you're essentially just driving based on human ability. And if you're kind of distracted or anything like that, then you hit something. I don't know how many people have hit like some car behind them while they reverse in a parking lot. But then if you have a newer car, then you have a like reverse assistance thing that tells you just starts beeping as you reverse. So you kind of paid for that level of like safety in a way, or caution, because then your car has some cameras at the back that help you to do that, to able to see what's behind you and avoid it, right? And these other things besides just simple factors of hitting another car. You're interested in staying safe, driving properly, keeping your lane. For the most part, some cars end up crashing or something because the driver went off maybe the lane a bit, and then when they try to go back, they went so hard that it flips the car based on the type of speed the car is traveling at. So stuff like that is avoidable, meaning if you have a car that knows how to keep the lane or can tell you when you deviate from a lane, if you are doing a certain level of assistive driving, then you are kind of in the good in that sense. So essentially why this work counts is we want to take down the numbers related to people dying on the roads in South Africa, because we now have if the technology exists, why not use it to push these numbers down, right? And the benefits are obviously more than just in terms of human lives. There's ride sharing saves money in terms of the economy. If you have 5 people driving their own cars to a place, that's a lot of like carbon footprint. That's a lot of money spent on just fuel from the individuals themselves, and the more like the likelihood of people crashing and so on, because each of them are in different mind states and everything. So ride sharing kind of goes with that, and we see a lot of that right now in North America, for example, where most cars are like Waymo cars are helping reduce fatalities and all that stuff. So yeah, and productivity obviously, and so on. And then as it stands now, if we look at the different levels of autonomy in terms of autonomous driving, there's level 0, which is just purely, it's your old car, you drive it, and you have to figure out everything. You have to anticipate and everything like that. And then there is a bit of driver assistance, for example, your cruise control, a little, your parking helper at the back when you reverse so that it knows and tells you when you get too close to something, and things like lane keeping and so on. So that's your level 2. Partial autonomy is kind of, I think partial autonomy is, okay, now the car helps in terms of taking control of the driving in itself, meaning some levels of cruise control would count as level 2 going forward. And then you have level 3 and 4, obviously, in terms of the spectrum, the lower levels are the human being is the most, is involved the most. And then the higher levels of autonomy are what we currently have, for example, with the Waymo cars, where you get into the self-driving car and there's no one else in the car but you. So that's the closest you get to level 5. I think they might call it 4.5 at this point in time. There might be some human intervention here and there or whatever, right? So as it stands, there's a lot of progress as a summary in North America, Asia, and Europe. Very little progress in Southern Africa, unless it's on technology that people buy with the car. So if you buy the latest model of the BMW, then it might come with some really cool safety features, really cool autonomous features, and so that and all that. But that comes at a huge cost that not everyone can afford. So we are trying to bridge that gap so that people can still get access to this technology at a lower cost. This is especially possible now because the models, the data are mostly open source, although the whole discussion around access and the ability to use it is still a gray area, and we will talk a bit about that. And then the other reason we want to then take these solutions and custom make them for Southern Africa is because in every jurisdiction or every country, the rules on driving are different. The signs are different. The people are different. The regulations are different. So almost everything is kind of different. So you kind of want to have a custom-made solution. Even just the ability of people to afford these things is different. So you kind of have to build solutions that are catered for the people in the area, right? So cool. That's where we are. So next, I'll just kind of discuss the approaches that we've kind of taken in getting closer to this dream. And what you see here is an example of a model that is a multi-model AI model. So what it's able to do, it's able to read, it's able to see and combine those two things and give you something that's pretty good. So meaning, if you run this, it's called the Microsoft Florence 2 model. If you run an image or something through it, you're able to get this really good descriptive definition of everything that the model is able to see. It does the segmentation, it does everything, and it can pull out words and so on. So you can imagine you want to be able to tell when you have to fork, when you have to yield, and so on. So all those signs are different, and you need a model that's able to see all that. So this is just kind of the utopia that we are aiming for, a model that's able to see as good or near or even better than what we see as we drive, because we are distracted as we talk to friends and so on in the car. So this is the goal eventually. So the key tasks that go into autonomous driving, I'll go kind of try and explain what autonomous driving looks like. The really simple level of it. It's essentially when you drive, you want to know where things are so that you can avoid them. And you're interested in how far things are, because something very close and something slightly far means you behave slightly differently, meaning you start braking if something is closer so that you don't end up hitting it. Meaning, again, it's obstacle avoidance. And what is the thing? Is it a human being? Is it a car? Is it a traffic light? All those things have different behaviors, and you want to treat them differently. So we are interested in knowing what are the obstacles, how far are they, and what are they really in terms of, are they moving objects? What else can we know about them? And then if I blink, will this thing have moved and be in a different location? Meaning I have to be able to anticipate and tell. And human beings do all these things very well to see, oh, this thing might be in the car, in the road, for example. Someone walking and someone running, two different things, and we are able intuitively as human beings to tell where that person will be in the next 2 seconds or in the next half a second. And then we will know when to slow down and so on. So that's another task we're interested in. And finally, where can I drive, right? So if I know where everything is, okay, where should I drive to get to where I need to be? So essentially, if you look at driving and just condense it to something simple, it would kind of look like this. Obviously, there's a lot of other factors into it. And as it stands, most systems that are autonomous driving or assistive use some variation of these inputs. LiDAR, which kind of throws beams of light and wait for the response to then tell how far things are based on how quickly does the beam reflect back or the laser reflect back. Then we know how far the thing is. And then camera, obviously, for detection to know where things are because that kind of mirrors the human perception system. Because human beings are visual animals, we see where things are and we can tell how they might act and so on. So that's why we have camera, and radar kind of looks at the heat maps in a way of where people are, or where there's movement based on heat essentially. And then we also have GPS so that you know where you are. For example, if you're in a self-driving car that's autonomous, you need to know where you are, or the car needs to know where you are to be able to properly navigate to where you need to be. So that's why you need GPS as well. And then obviously the map, because just GPS on its own can point to places on Earth, but it's not obvious that you can drive. It's not always, it's especially not the case that you can just drive straight from one point to the other. So you kind of have to navigate where there's roads. That's why you need a map on top of needing GPS. So GPS tells you just where you are relative to the place. And then the map tells you how to go about it, because some places are not roads and some places are. And at the end of the day, you do need some way of knowing what the car is doing. So you are interested in the car parameters. So if you put all these together and you have a big neural network somewhere there that handles all these together, you are able to then decide how to steer the car, how to slow down or speed up to get to where you need to be in the right place, in the right time, and right condition without crashing into things. So essentially, this is the goal, right? So yeah. So now that we know what the goal is, now I'll show how we are kind of going around that whole thing, because we are not in, we don't want to buy LiDAR, we don't want to buy expensive cameras, we don't want to buy radar and all these things, because most of these are so expensive that you cannot even start doing the work in Southern Africa because the cost is just too high. So what we want to do is, okay, how can we use software to get close to a similar solution? Even if I get to 80% of the solution, I can save some lives. I can save someone from crashing into the car behind them as they reverse, if I get to even just 80% of the real solution, or even 50%. So that's what we do. So we start off the tasks that we focus on. Object detection, meaning we are interested in knowing where things are and what they are, right? And drawing a bounding box around them so that we localize where the things are. And the images you see here are essentially just that. You see, we're able to tell people apart on the road, cars and street lights, and as well as traffic lights and so on. Even at night, we want to still be able to see where everything else, we still want to see where the traffic lights are, all the cars are and everything, so that we can avoid all the obstacles that we have in front of us, right? So this is just a view of what object detection looks like. It's the what and the where it is. And then secondly, we're interested in knowing how far things are. So on our end, we're not going to buy LiDAR. It's expensive. So what we're going to do is use almost a filtered version of it. So some people collected LiDAR maps in the past, like depth maps based on LiDAR, and trained neural networks to be able to predict the same thing as the LiDAR at some point. So we are going to use that neural network instead of buying LiDAR to do the same thing, to figure out where things are relative to the camera in our car, right? So with molecular depth estimation, it means we are using one camera. Primarily, this is done with LiDAR, like I said, which is a hardware thing. When it's camera, it's mostly multiple cameras that do this. And even then, a company like Tesla, for example, they say they use camera only, but that means only in inference, meaning only when you actually drive on the road. But for training, they do use some data from LiDAR. So we are essentially kind of doing the same thing. And LiDAR is expensive. So that hence people are more interested in moving away from that, right? And recently I saw that, this was an interesting thing, I saw that Volvo decided to install LiDAR systems in their cars in their cars that they'll release in 2025, just to enhance safety. So it's an interesting thing to me that in 2025, they are still investing in hardware, whereas we are like, okay, we are doing software only. It's interesting that it's so important for safety that they would pay that money to do that. So that's why we need LiDAR as well. And the images you see essentially show how far things are relative to our camera. And you could see on the top image, the red is closer to where the camera is. This is a dash cam. So everything very red or maroon will be closer to us and blue will be further. So you want to be able to know that so that you know when to stop and how to avoid things. On the bottom image, you'll see that we see where the cars are, but an interesting fact is you cannot see the potholes because depth in this case does not give us the potholes. It does not give us the real 3D or geometric definition of the surfaces. So we don't even see the potholes based on this. But a human driver would be able to see these during the day, meaning just combining where things are in terms of object detection and then how far they are is not enough for us to be able to avoid things like potholes on the ground, because then it doesn't pick them up. So we need something extra to be able to pick up, oh, here's a pothole, let me avoid it, right? And that's where we use surface norms. And these are pixel level, meaning with surface norms, essentially we are looking at every surface and trying to tell what is the 3D structure or orientation of this object, right? From just a 2D image. And this obviously would have been trained from real data that has the real 3D definitions of or orientations of objects. And suddenly when we do surface norms, the potholes just pop up. And now if you combine depth and then the surface norms, now you know how far things are and where the potholes are. So that's kind of why we need all these different things, right? And just on the right top corner is just a view of if we combine surface norms and object detection, this is what it looks like. And this is normally the view you would see if you get into a self-driving car. You would see something similar to this with like a green light in the middle to show this is where you drive. So it's yeah. And then finally, we want to be able to detect, to predict this. Where can I drive? Now that we know all these things, we know how far things are, where things are, how are they moving based on optical flow. What is the real surface? Meaning we are able to even pick up, potholes and so on. Then we want to know, where can I drive? Because knowing the lanes, knowing everything around me, where can I drive? And we want to be able to map the drivable road, as you see in this area. In this image, the green speaks to you might be able to drive here, right? I mean, and this is a very bad current version of the model we have. This is what it would show in terms of, okay, you can drive here. But as you can see, we have some issues around that. For example, sometimes there's because we are using a dash cam, sometimes there's a reflection of the road on the bonnet of the car. And then the model, because the model we are using is trained from elsewhere, pre-trained from elsewhere, it ends up predicting the road on our bonnet. So these are kind of the challenges we have to look around and solve. And this here is just an example of what it would look like if you do, if you're trying to see how things move around you. So essentially optical flow. It's a very bad version of it, but we get into a better version soon. Okay, so the real challenge is to getting to where everything is, or something that works better than what we currently have, is compute and storage is expensive. To be able to work on these kind of problems, you need a lot of data for training these models, or even just fine tuning. You need a lot of hours of driving video that you then annotate, which is money. So just storing these video clips is money, because you have to store them somewhere. Your computer does not have sufficient storage most of the time. So you have to store them somewhere on a Google Cloud or AWS. So that's kind of money. So that's one of the challenges that I learned recently, that, okay, just storing like 100 videos that are 3 minutes long is a lot of money to begin with. Secondly, running these things or even just fine-tuning or training them is computationally expensive. So you need GPUs, and you need good GPUs if you want to iterate fast, because your normal computer will not be able to do that. And this is something that's not spoken about enough, that if you are in, for example, academia, you might get access to these GPUs for free, not for free, but if you pay tuition, then you get access to these GPUs at a school. So people at the schools are more likely to have these GPUs, but most of the time they use these for just, they will use them for training a model and deploy it, and then it's over about that paper. It hardly or rarely ever goes on and on and on, so that they build an entire system or an ecosystem around something that other people can then start using, right? So GPUs are a big thing also. And then finally, to be able to annotate the data and do everything requires time, meaning you might have to hire some people to do this, to even just annotating from scratch or just checking the data and figuring out if everything is okay, right? And then there's the human factor. Human beings make errors when they label data for the most part. And that's one other issue. If you are on a budget, it means you might hire people that are not as qualified or that are not as motivated, meaning you end up with, and the metrics you might employ are based on how many images, let's say, they label. So these people might end up just clicking, and you get a lot of labeled data, sure, but the quality of that is questionable. So those are the issues around that. And then lastly, modalities, because everything that goes into a self-driving car or that kind of system, an end-to-end system, requires a lot of different modalities of data. You need 3D data, you need depth level data, you need classification, and so on. So all these things that are required and requires different skill sets at the same time, or different models. So that's another challenge, right? So what we think we want to do, or what we've currently done so far towards solving this, is firstly, we want to be able to, okay, how can we improve on this problem, but iteratively on a low budget. So we don't have money to hire a lot of people to label our data like your Google can do or OpenAI can do. So what can we do to get to even just 50% of the results they get? So firstly, we want to be able to do this in an automated way, label the data in an automated way. How do we handle the label noise, right? Because there will be noise that comes from the labeling we get. If we use, either we use models to label our data, which is pseudo labels, but then there'll be noise in that. So how do we handle that? And then in terms of time, how can we set up our everything, meaning collecting the data, annotating the data, training or fine-tuning the models, deployment, and then iterating over that? How can we do that in the fastest way possible so that we keep up with everything that's happening, right? That's another question. And eventually, what model do I even use, right? Because there's so many models for everything. Classification, there's 100 models. Depth estimation, there's 100 models to pick from. And each of these models are of different sizes. Some models are the large model, which require you to have a lot of compute. Some are smaller, but the performance is not as good. So that trade-off is often not very well discussed in terms of how do practitioners eventually pick what to do. Because in research, it's, okay, I'll just pick the best model, the best performing model, I'll show that it's good. But then in reality, you have to factor in a lot of other things like the cost and everything. So that's why it's important to figure out what model to use, right? So in that direction, figuring out what to label, how to train, how to handle label noise and everything, we worked on a paper where what we did is compared the traditional way of doing this to a way where we let the model pick what samples to label. And then based on the labeled samples, we improve the model. So essentially the model picks the data that improves itself in a way. Instead of, or the model picks the data, the human being labels, and the model improves. So it's essentially a collaborative thing, and this is called active learning, right? The traditional way is you collect images, you manually annotate, you check for quality, you store the data somewhere, you train a model. And then now you deploy this model and just monitor it. And maybe some other time in the future, you update just to make sure there's no drifts in what the model knows and any new information. But then what we are interested in is okay, we know we have the models that are trained to some extent. How can we use those to give us new labels or hint what to label to be able to improve faster? So essentially how this works is we start with a lot of images that are not labeled. We select some of them based on a certain model. The model tells me, no, I'm not sure about these images. And then the ones that the model is not sure about, wherever the model, the AI is not sure, those are the images I take and I show to the human labeler or the oracle, essentially. And the human kind of looks at it and says, no, I would have turned left here. I would have turned right here. I would have done this here. And then I then take those and feed them back to the model. I'm like, hey, your friend, the human being, has told you what to do in these cases. And we want to do that because we don't want to label every single image because some may be trivial to the model. So we want only the ones where the model is unsure. Those are the ones we want to pay for labeling. So we pay someone to label the hard ones, and then we improve the model, and then it's an iterative process, right? So that's kind of what we worked on. And we looked at that and kind of just looked at, okay, but now sometimes the people you hire, they get these things wrong. What do you do in that case, right? Because they do have some other problems like fatigue. Sometimes they're just not experts in the thing. So, or just human intuition, they just got the thing wrong. But we want our model to be good regardless. So then we want to look at, okay, now that I know how to label the best examples to improve, how do I then feed them back? How do I choose these, given that the person might be wrong? Meaning I have to kind of cater for that. And we worked on, we looked at a couple of papers in a review and wrote a review paper just exploring this literature around this problem. And we found that the biggest challenges are that this iterative process, especially if you have big models, is computationally expensive. So it costs a lot just to redo everything over and over again. And then there's bias in it. And then some of these things don't have a realistic measure of how good is this really? Because most people in literature will kind of pick hyperparameters for their model that make the performance of their model look better than all the baselines. So it doesn't really reflect to someone entering the field and asking the question, okay, what model do I use? What should I do? Because then everything else is kind of biased to boost performance in one way or the other, right? So that's why we kind of and then we decided, okay, based on that, we have to look at application-specific models, ways of picking samples. We have to look at user-centric active learning, meaning active learning that speaks to the model, meaning when we have a couple of images or videos, to decide what to give to the human being, we decide based on what the human being will understand, meaning we show them the images that the model is bad at, and then we say, oh, yeah, it's bad at this because it sees 5 images as 5 cars instead of 7. So those kind of things, so that the human being does not have to guess at what is wrong. They kind of already get an idea of how to improve the labeling we need, or agree or disagree with it, right? And that requires that you integrate LLMs into this process. So we kind of looked at this, and eventually we're like, okay, this is the direction we need to take. And so we worked on a paper that relies largely on the transformer, which is the kind of neural network architecture that's kind of driving most of the things in language, your ChatGPT and so on. The transformer is kind of the thing that's driving that. And what we figured is, the transformer is trained, most of the transformer models are firstly trained in a self-supervised manner or on a data set that is clean. So most of them, for example, would have been trained on something like ImageNet 1K. So we are like, okay, it's trained on sufficiently clean labels or in a self-supervised manner, meaning it knows what an image of a cat is compared to an image of a dog, even if you don't tell it this is a dog and this is a cat. So semantically, it can tell the difference before anyone tells you. So we are like, okay, if I have a model that knows the difference between images before I even tell it what the image is, if I can use that as kind of a filter, meaning if I give a human labeler an image and they labeled it as a dog, but it's actually a cat, then my model will say, no, this deviates too much from what I expect. So that kind of is what we proposed in terms of handling label noise in this scenario using a transformer, so that the model can say, no, what you're saying is too far from what I expect, knowing what I know. Then the human being gets that suggestion, and then we are able to select samples where we are then able to select samples that the model is not sure, but at the same time, the feedback of the human being gets discounted if it does not agree with the model. Yeah, so that's that. And this paper is currently under review, and you should be able to see it come out soon. And then we've also figured, okay, the other problem is, what model do I use? Because there's a million models on Hugging Face, for example, to pick from for different tasks. And just for the task of depth estimation, there's 162 models on Hugging Face. And some of these you might find vary in size, so that there's one model, it has 3 different variants: the small, the tiny, the big, or the base, or the large. So it's quite hard to figure out. If you just pick the large model, you might not have the compute for it. So if we're in Southern Africa, we have to consider these things. It's unlike where you just see a model that performs well, you're like, oh, I'll just use this and go ahead. So essentially, we are aiming to guide the actual practitioner. How would you go about this problem? And this is a paper I worked on with Andy at the Shard, just looking at what models can we deploy and what is the impact of label noise, given we have a small budget, right? And then what we did is we essentially set up a couple of models, swing transformer models for classification, and then some YOLOS models for object detection. And we had all the different variations, the tiny, the small, and the big models. And we looked at how do they perform if you give them noise, right? If the labels are noisy, how do these perform? And what we found is that, obviously over 3 different data sets, we use CIFA 10, CIFA 100, and the BDD data set that's mostly used for autonomous driving. And then what we found is that it's not obvious that bigger models always perform well. So you'll see that in the, I'm not sure if me zooming zooms this, but in the results section, so the graphs that you see at the top kind of compare these models. And what we essentially found is that sometimes even the big models, if you put noise, they end up performing exactly the same as the smaller models if you have a high enough label noise rate. So essentially, at some point, depending on how much noise you think you have in your data, it is not obvious that you always use a big model. Actually, sometimes the results are kind of go the other way around, so that a smaller model is less likely to just go haywire when trained on noisy data, because it's not even able to overfit. It's not big enough to be able to overfit eventually when you do this. So yeah, that was an interesting result that we found. And that goes back to saying, yeah, you cannot directly just take models that are trained in North America and just try to apply them in South Africa and have them working exactly the same. Oh, sorry. And then secondly, we looked at, okay, now that we know that all these things, we want to help the person labeling the data. Meaning we want to use vision language models, meaning models that understand both vision and language, so that the model can be able to kind of, we show an image, the model predicts what it sees. So for example, in the image you see now, this is what the annotator would see. The minute they are presented with an image, the model would then, a couple of models, not just one, would predict what it sees.
Yeah, I just wanted to say about 5 minutes. We're getting
Okay.
almost, yeah.
Okay. So the model will predict what it sees, and the person just has to either agree, edit the annotations, or show me something similar so that I can decide, right? So that's what we looked at, and we kind of ran a review on this. We wrote a review paper on this, just looking at publications from 2012, 2024, tasks that go from image to text to figure out what can we use to do this, right? And then eventually we found that most of the works that exist don't do that. The closest thing to what we need is these big models from Facebook and Microsoft, Florence 2 and the SAM model. And what they did instead of taking different models and having different predictions that add up to something, they have the capacity to take all the data, put it from the beginning, label it all in the way they want, so that they train an end-to-end model, so that they train a model that just, you give it one image and it can tell you a lot more than just where things are. It can tell you where things are, what's happening in them, where each bounding box is, where segmentation is. So they combined all these tasks into one thing. But to be able to do that, you need to be able to have all the labels up front for these. And what they did in this paper that we kind of copy from is they use pseudo labels for some things. So they use other models to label, like other very good models to label the data they need to use for this big task. So what they did is that, and then we kind of copy that in the work we do going forward, right? And this is just some industry solutions for labeling that we came across that could be useful to people who are working on computer vision problems. And especially Enabler, I think, is a South African company, so that was interesting to find. So coming to where we are now on the data set we are building, the data set, we call it SA Lens. Essentially, it's a vision-based data set for advancing autonomous driving in Southern Africa, right? And this is ongoing work. It's in collaboration with some guys at Leeds University, BMW South Africa, and one more guy at the University of Pretoria in the engineering department. And what we did is we essentially went and said, okay, let's collect some data using these dash cams and build this out using pseudo labels and human intervention here and there, build something that helps the human labeler make their labeling much faster or correcting their pseudo labels. So that's where we are. We're focusing on Pretoria, Hatfield, Centurion, Sandton, and Midrand, because just these are closer to where the people I'm currently working with on this are based, right? Currently, we have 2 cars that are doing this using dash cams. The dash cams were pretty cheap compared to what's being used out there, 1 to 2K per dash cam. We currently have 1,000 15-second clips, each at 25, sampled at 25 frames per second. So essentially almost 4 hours of driving. That makes up 375,000 images, HD images with pseudo labels. And then we are currently working on the platform to make it easier for human labelers to then correct the labels or just confirm some or throw away some, so that we have more robustness for testing and everything. And this covers all the tasks: object detection, optical flow, surface norms, depth estimation, and drivable area, right? And we just kind of compared that to the data sets that exist on this, and we found that there isn't really anything in South Africa that covers the kind of data set we are trying to build. Anything that covers South Africa is an effort maybe from Europe that includes some portion of South Africa, mostly Cape Town. So we decided to build something from scratch entirely. Right. And then conclusion, essentially at this point, we figured we need to use some NLP to make it easier for human beings to understand what the model understands, and for human beings to then feedback what they understand to the model, or query the model based on language. So that's the key thing. Labeling needs to be closer to where it can help the human being, meaning language is the easiest way to do that. Hence, ChatGPT and so on have been so popular, right? We need to be able to do that. We need to look at different model architectures and make sure that we can leverage everything. We need to improve training using self-supervised learning and any other models that exist in terms of fine-tuning and so on. So essentially, and then what's next? Self-supervised learning, we think that's the future, together with human feedback or pseudo labels, right? More unification of modalities, and this is happening because of the transformer, where everything is now treated as if it's just words, and you just put it in and it works. right? And then we think what comes later is models will eventually become cheaper, compute will become cheaper, more accessible, but the skill set still lacks a bit because some of these things, you want to use it, but it's so hard to even just get it working on your system. So those are the kind of the things that we are looking to improving. And obviously safety and alignment eventually would be what we will look into for ongoing research. So yep, that's it from my side. And thank you for the time. I will open up for questions.
Okay. Yeah. Thanks. Thanks so much for those for this presentation. I think it's on one side it's showing kind of the current limitations of current approaches, and then also how you localize. And for me, the thing I really also like is thinking about, okay, what are the innovations also in the data set collection that you can do, right? As opposed to just sitting and saying like you're waiting for the perfect, but then what else can be done in these spaces? And also then thinking about the annotation side and how the annotators access that the kind of this content, and then maybe also using state-of-the-art systems to act as annotators. The big, like, maybe I think I wanted to find out sitting in this space is just, you know, for practitioners out there, what should, like, you know, they really be thinking about as you're saying that, okay, look, compute will go down over time, but then you need these core things. How, like, you know, what kind of mental model should they have in working in this type of space? And then, yeah, but just while you're thinking about that, for anybody on the webinar, if you would like to ask a question, please raise your hand. And then once I acknowledge you, you'll be able to unmute. If you don't want to ask it yourself, you can put it in the chat. Yeah. Okay. Yeah. Go ahead, Moseli.
Yes, yes. Okay. So I think practitioners in the space, I'm going to try and split it into two a little, just so that it's like, okay. So for people starting out, what I find is, or at least from the position I look at it now, for people starting out in this space now, it looks like it's so hard now to make any progress, at least from my end. Because when, like, at least when I started this back then, Facebook and all them were not so big that whatever you do looks like nothing, right? So that's the one part of it, that now the level or the barriers of entry, not necessarily the barriers, the level at which you have to enter is much harder because everything is just so good now. If you're working on anything in NLP, it looks like what you're doing is not that good simply because you're comparing to a multi-billion-dollar company, right? So that's the one thing that I think can easily discourage people. And to that, I would say they should always think that even back then, before those companies came in, there was still research. At some point, AI was a thing that wasn't working. So I think people should always focus more on, okay, what's not working? What is not being addressed in AI? Focus more on that space and see how you can start off in that area and use whatever exists to help you, to help speed up whatever you're doing in your area that is untouched. So that's the first thing in terms of the newer people, people who are new to in this area. And then secondly, people who have mostly worked in this area for a while and are looking to make impact or switch around. I think currently I would say collaboration, that's the first thing. I will highly highlight collaboration because it just makes everything in terms of starting in any one area pretty straightforward or easily accessible if you collaborate. And then that has a effect of skill sharing, because if you collaborate, you get a lot of, oh, here's where you start and here's where you get this and all that. So I think that's kind of where the two main things I would highly emphasize.
Okay.
I'm not sure
Yeah. Thanks for that. There's a question here that comes from Idris. He says he might have missed this, but did you employ LLM assisted annotations? Because annotating data manually may be impractical, but then also might require a lot of money. So how did you guys get over, or get over that, or how are you thinking about that?
Okay, so what we decided to do here is, no, instead, because we are trying to go for scale, meaning a huge data set, we decided, okay, we will use pseudo labels and only correct a certain portion of them. Right. So pseudo labels, meaning we look for the best model in each modality, meaning we look for the best object detection model, the best optical flow model, the best depth estimation model, the best surface norm prediction model. We look for those and employ those to get the best labels we can get. And these are pseudo labels. We are aware of that and we understand. But then what we then do over on top of that is, because we are doing everything using like in an active learning framework, what we are then going to do is we will show some of these images to human labelers, but we will only pick the images that the models that we used are unsure about, where the model is like, yeah, I think it's 5 cars, but I'm not sure. Those are the ones we then show to human beings, so that human beings then just kind of confirm or edit. So essentially, this slide speaks to what we decided to go for. Meaning, eventually, manual labeling for segmentation, you can imagine, means drawing points around each object. But in this case, we are like, no, we're going to use a model that already does segmentation for cars and everything. It knows where parking spots are. It knows what things are. We're going to use that and then just allow the annotator to then say, yeah, everything is correct, accept no annotations, or no, edit. Then they only need to edit like 1, maybe bounding box or 2. So we are kind of just trying to speed it up by using 1, pseudo labels, and then 2, make it so that models can communicate to the people by using like vision language models, so that they can understand. The human being needs to just read and be like, oh no, it's wrong. So that's kind of how we are going around that. So at the end of the day, we are aiming for something like, if you have, let's say, 100 images, we are trying to only label 10 of those.
Sure. I think a quick one. Yeah. I think a quick one that's connected to that from Idris is just asking, so is it also used for evaluation, or use the pseudo labeling as gold labels?
So we use pseudo labeling just for improving the models, but then what human beings eventually label, that's what we will use for evaluation eventually. But then since whatever we are using, the models we are using are already custom made for other data sets, we can then go back and take these same models and test them on like official data sets, like your COCO, we can always test them on those because they are already like set up for that.
Okay. Thank you. Are there any other questions? Anybody want to unmute and ask a question before we go to more written questions?
Yes. Hello.
Yes. Oh yeah. Just introduce yourself, because your name is and then you can ask a question.
Hello. My name is Tabang. I just want to know, thanks for the presentation. It looks really good. For instance, I've seen you spoke a bit about potholes and stuff. Isn't that something you can just ignore? Because I think it can maybe divert the main purpose of what you're trying to do. Like, I feel it's an incompetency that you can avoid. Potholes and maybe undone roads. Isn't those some of the things that you can just ignore? The second question is, do you see any usefulness of using multimodal learning? For instance, you have radar, GPS, like the camera. Do you see any usefulness? And if so, what sort of direction do you think that can be useful? Can you say something about that?
Okay,
thank you.
Yeah. So, thank you for the question. Thank you. Really good question. So to start off, in terms of the potholes, for example, or unique areas where it's not so clear what to do, I think the main reason is, so if we assume the roads are exactly the same as what the data was trained on, meaning, for example, in South Africa, sometimes for the most part, depending on where you live, the traffic lights just don't work. So if you are to make a system that kind of decides whether to move or not based on, it's trained on a place where traffic lights work most of the time. So you have to be able to cater for that if you are to kind of adapt the model that you have to be useful in the area that you are going to use it. So meaning in South Africa, if we ignore potholes, then sure, we can just apply a model, but that would almost be the same as treating South Africa as if it's the cleanest, or like it's the best place to use AI, right? So meaning it kind of goes besides the point a little, whereas we want to show why exactly we need to retrain, especially showing the edge cases like, oh, these potholes here, if you do this, they don't show. If you do this, then they show. So that's one thing. And the reason why we do that is we don't need to label the potholes. As it stands, we have the data for that in South Africa mapped out in terms of where the potholes are for the majority of South Africa. And luckily, we have that collected long before. So a friend who worked on something long before kind of has that data, not up to date, but we have that data related to GPS already. So it's kind of a free thing that we are saying, oh, let's pull it in because we already have, right? Meaning we can then map that to what you see as you drive, as well as what your GPS tells you, oh, there might be 5 potholes coming based on this other data that we have. That's not necessarily what we are collecting now. So that's the only reason we are really comparing them, because at night, if you're driving, the AI will not be, let's say you're using the system, you are driving yourself, but you need it to warn you. The AI, if it's at night, if the vision is not so good to see potholes at night, we want to be able to then pick them up from the GPS if we have that data, where it has mapped, we have that data mapped from BMW or wherever. So that's the reason we are pulling that through. And then secondly, using multi-models in terms of LiDAR, radar, the only reason we are not doing that for now is essentially the same as what Tesla say in terms of using that. It's at scale, it's not feasible to use that everywhere. So meaning in this case, we can buy that, but we don't even have the kind of money to buy LiDAR systems and multiple cameras that have the best solution, right? So we're starting from somewhere. We are saying, okay, we want to work with, okay, can we make something work with a dash cam? If we can do that, maybe then we can, there's people who might be interested in this work, help with funding and so on, then we can then expand and include other modalities that may be cheaper to go into next. So camera with a dash cam is the simplest. Most people will have access to that through their phone or a dash cam. So we want to be able to provide for those people to start off with, and perhaps later on, or developers to be able to use our systems to do that for people. Later on, if this work kind of actually works, then we can expand into other modalities, if that makes sense.
Okay, thank you for that.
Yes.
Any last questions? Somebody wants to unmute and ask the question? Okay, I'm gonna take it that there's none. There is one more from okay, there was one. Was from Tope. It says, are the most informative data points the same as the ones that the model is struggling with? I think that's what he means. And then another one was from Idris, who just said, how valuable are the existing data sets when it comes to South Africa?
Okay. So, okay, let me see, which one do I start with? Okay, are the most informative the ones the same as what the model struggles with? Essentially, in terms of that, we are measuring uncertainty in this case. So we look at it in the sense of we measure usefulness in terms of uncertainty. There's multiple ways to measure like usefulness or information. But if you look at information entropy then and use that, then that's the way we are saying if the model is unsure of it, that's what we need to label, because there is a lot of variability that the model does not really understand. So we want to label those so that we add more information on those. So that's one way, but there's other multiple ways to look at it. For example, the approach we came up with that uses purely just, okay, we are looking at samples that the model is unsure of, but also the oracle labels them in a way that kind of deviates from what the sample the model understands. That's one other approach. Or you could just look at there's different ways to split that, but essentially whichever way you measure information content or uncertainty in that could work. Right. And then sorry, the second question, because he was?
Yeah, the last question was just that how valuable are the current data sets to the South African situation?
Okay, so the current data sets to South African situations are, I think the way I'll speak to that is that the data sets, majority of them are based on the place where this work is based, right? So most of this work has been done, sorry, I'm just trying to get to, most of this work has been done by private companies, not researchers per se, individual researchers, simply because of initially the initial cost of starting to do this research was highly expensive. Buying the LiDAR and everything, that's expensive. So this has kind of set in the private sector for the most part, because they're looking to make money in this. So that's why Waymo is owned by Google. Most of the data sets will be owned by some sort of research lab or a research lab within a profit-making company. So that means they are focused on the areas where they will eventually deploy their self-driving cars and make money, right? So very little of these data sets include scenarios in South Africa that are very unique to South Africa. So that's how I can put it. Only a few include some portions of Cape Town. Thanks.
All right. No, thank you. I think that this could go on for a long time. I really want to thank Moseli. Yeah, in his time zone, it's very early in the morning, or he says it's late. Maybe given the way that he's maybe a night owl. Thanks for joining us for this. For everybody else, just check the chat. I put in some links for the Design Justice AI Institute, and then also our workshop. And if you are not connected to us on our social media, please do. Yeah, we have a lot of places where you can follow us. The recording for this will probably be available, if not later today, probably on Monday. You can check our YouTube for that, and then we'll try to also publicize it. Thank you again, Moseli, and thanks everybody for coming through. And yeah, we'll see you guys in the next webinar. Right.
Thank you.
Thanks everyone.
Thanks everyone. Thanks, Fukosi.